Hey, confused on all the oxygen-based functional groups that you have to know for organic chemistry? Well, I got you. We will be going over their structure, nomenclature, and usages. This is alcohol. It is simply an oxygen attached to a hydrogen. It can conduct hydrogen bonding and drastically raises the melting point of a molecule. It also turns a molecule into a polar one and also a hydrophilic one. It is found in chemicals, vital and biochemistry such as glycerol or sterols. Ethanol is also the alcohol that people drink and is also commonly used to extract phytochemicals. All alcohols either begin with hydroxy or ends in ol. Simply depends on the functional groups which are also present inside of its compound. This is an ether. It is connected to a side chain or an R group or an alkyl group and also the main carbon chain. To name it, you simply just gotta know the side chain's name and then you end it with an oxy. It can't conduct hydrogen bonding, nor does it actually cause the molecule to turn polar unless it's a lower ether. They are generally unreactive, making them ideal solvents. The only way to break one is for electrophilic substitution. They also generally smell really sweet. This is an epoxide. All start with epoxy or end with oxirane. They are structures in which a single oxygen receives a bond from two carbons adjacent to each other. This forms a ringed compound, only with 3 different participants. This isn't ideal in cause of strain, as according to Bayer's strain theory, and also Pitzer's strain, in which this molecule is just so rigid that it can't bend around to fix this angle of an issue. As according to Vesper conformations, the carbon should be at least at 109.5 degree angles when bonding to their substituents, but the oxygen forces them into a 60-degree angle, thus making this not ideal and heavily strained. Alright, now we have carbonyls. These are one of the most important groups to the numerous reactions that they can conduct, especially in enol, enolate, and aldol forms. They cannot conduct hydrogen bonding themselves, they need a hydroxy group to help them out. Lower ketones smell sweet, but eventually lose their smell with higher carbon counts. Lower aldehydes smell horrible, such as formaldehyde. Higher aldehydes smell sweet. Now you might be confused. Okay, well let me elaborate what these subvariants are. Ketones are secondary substituted and end with 1 or start with oxo. Now, aldehydes, they are primarily substituted and end with al or start with formal as a prefix in ringed or non-main chain carbon groups. They can also start with oxo if it is on the main chain. Okay, so there's carboxylic acids. They all end with oic acid, and will always end with oic acid as they are the alpha functional group. They are the most dominant. It can conduct a tremendous amount of hydrogen bonding and conducts it with itself via dimerization. They are good electron withdrawing groups as their resonance structures usually drag all the electrons towards their regions and away from the rest of the molecule, just like ketones and aldehydes. They have a sour smell, such as vinegar, especially at lower carboxylic acids may contain a pungent odor such as rotting fruit. Now, carboxylic acids act as a template for a whole slew of other functional groups. See that alcohol group instead of the carboxylic acid? Yeah, that could be replaced by other functional groups. For example, acyl halides, or when a halide replaces the alcohol, this allows for an easy transfer into other groups such as esters, which instead of a hydrogen are connected to carbon chains. There are also acid anhydrides, which are a result of dehydration synthesis. There are also amides, which are when aminos replace the alcohol group. And if you really think about it, replacing the alcohol group with a hydrogen or carbon chain leads to an aldehyde or ketone group. And what I would like to mention is that carboxylic acid and ketones and aldehydes are such good electron withdrawing groups, it's because oxygen is extremely electronegative. That means when a double bond is nearby an oxygen, the oxygen usually takes the double bond, because the double bond with the oxygen is a lot more stable than a carbon-carbon double bond. An example would be peltamerization instead of ketones and enols. They can also be protonated to become better leaving groups since they are so dense in electrons, they are often serving as a base.